Hi, everyone. Thanks for joining us today. I'm Kim Coleman-Madsen. I'm the FirstNet Public Safety Broadband Program Manager at OIT. This is a technical assistance workshop through DHS OEC. Two minor things I was asked to share by OEC. Number one, we have a few vendors in the room. Thanks for joining us, but we'll also ask you not to ask any questions. This is really meant to be focused on state and local government, and I don't think I have any tribes here today. And then the other thing I was asked by OEC is to qualify that the model or the software program that is being used by Rob is not necessarily endorsed as a program by OEC to be purchased by government. So that being said, thanks for joining us. There's bathrooms are down the hall past the elevators on the right. We're going to take a break about halfway through. It'll be a single break only. We'll try to get you out of here as close to 12 as possible. There's some coffee, water, and minor refreshments or light refreshments in the kitchen right here. And I'll introduce Rob Dew. He's with SAIC, part of the OEC ICTAP name and acronym program.
You can't get away with it with government topics. Yeah, so good morning. As Kim said, my name's Rob Dew. I've got about 20 years experience doing wireless design and deployment, mostly on the commercial side, international. I've worked for Nextel, been a contractor to Qualcomm, Ericsson, Vodafone, Telefonica, some of the big carriers around the world. The last 5 years, I've worked at SAIC and been primarily focused on wireless priority service and emergency communications for federal, state, and local public safety. The agenda is we're going to go through a little bit of an overview. I know there's a lot of technical people here, so I'm sorry if some of the basic stuff about LTE and kind of why you would do an LTE public safety broadband network. Maybe you've seen it before. We'll go a little bit into user requirements, a little bit of some of the infrastructure components in part 3, you know, the different type of cell sites. I will say that this is very much focused on the radio access network, so it's really focused on the eNode B or the cell site. There's a whole other part of the network, the evolved packet core, which is the core network. We'll touch on it a little bit, but this is really focused on the RF side. We'll go through using the public safety network, you know, some of the applications, some of the devices, some of the provisioning, security aspects. It'll be at a very high level, but hopefully there'll be enough keywords on the slides and references that you can go get more information if you like. And if you have any questions afterwards, you know, feel free to email Kim and she'll get me the questions. There's a couple slides I did update last night that I'll show up here, maybe different from your package, but I'll send in a soft copy PDF after we're done. And then we'll finish up. You're asked to do 3 counties in Colorado, kind of a mock LTE design. I'm going to try not to go too much down in the weeds, but I want to show some of the different coverage levels. We'll get into things like SINAR, signal interference to noise plus ratio. We'll get into RSRP, some of the very high-level RF concepts that you want to know when you start looking at doing coverage and capacity planning in Colorado for an LTE public safety broadband network. So Jason Matthews, we'll introduce him in a moment. He's going to cover the first 3 topics, and then I'll jump in on the 4th one. So go ahead and start, Jason.
Thank you. And you just want to advance the slides?
Yeah, I'll do that. Yeah, that works.
Okay, good morning. My name is Jason Matthews.
No, go ahead. I was just
again, my name is Jason Matthews. I'm with the DHS Office of Emergency Communications Technical Assistance Support Team. I come from Central Florida, and I've been working with the OEC TA team for about 4 years, doing communications exercises, COMU courses and support, as well as most recently broadband outreach as well, getting into the broadband side of things, and getting to learn a little bit more about that and starting to kind of explain some of my trials and tribulations with it and some of the things that we're doing. My background is operational and technical. I've been in law enforcement for about 15 years, as well as EMS over on the East Coast. So I'm going to take you through the first 3 sections of the program, looking at kind of a high-level overview of what public safety broadband LTE looks like, and some of the different types of network topologies and things that we have coming down the road.
Get it back in presentation mode. Yep.
Do have a little bit of a dry throat this morning, so I'm going to keep my drink up here.
Do you want to just make sure everyone on the bridge can hear you? Just
yeah, absolutely. Can everybody on the bridge hear us okay here?
Yeah, sounds good from this end.
very good.
Yeah, we probably need to get into back to presentation mode for this one. Okay, perfect, thanks.
Okay, this first slide here is kind of where we are today. Mission critical voice occurs over our VHF, UHF, 800 and even 700 megahertz radio spectrum. That is our primary mission critical link. And I apologize for the laser pen, but it's going to kind of be hard to see. It is a little green dot there. So this is where we are today with our mission critical voice occurring over our legacy land mobile radio systems. A good majority across the United States, public safety data networks and data applications are running across today non-mission critical circuits. There are some exceptions to that. There are some folks, early adopters, and some folks that have legacy narrowband data technologies that are still around, are still being used. But a good majority of us out there are using these non-mission critical networks for that, which means we are competing with everybody else that's out there. Our subscribers are just as equal to anybody else that's out there on those networks, be it across any of the national or regional carriers. So this is kind of where we are today. We also have our commercial 2G and 3G voice communications that are occurring over a smartphone. I don't know any public safety responder that are not using some form or fashion of a combination of these technologies today to get their missions done. Whether this device be a personal device kind of being used in a quasi-work role, or whether it's a agency where folks are actually carrying a multitude of these different devices all at the same time. So this is kind of where we are today. Using those commercial networks, we are apt to site outages because these networks are not hardened to public safety specifications. Site outages, congestion, different things like that occur on the network when lots of folks come into an area and may overwhelm a certain group of cells or certain sectors on a particular cell site. Coverage is also a concern. Coverage is not always necessarily going to be where public safety entities are going to need that coverage. Okay, our immediate goal with public safety broadband is to create a methodology for us to move away from, or at least have an additional layer of mission critical data for public safety. So this is our first goal, is to be able to have mission critical data as we see these lines into the mission critical world, actually for data side turn from non-mission critical into mission critical. That's our first goal with public safety broadband. Coming a little bit later on is going to be our end goal of reaching the time when we can actually have mission critical voice and data occur over that national public safety broadband network. Okay, for those that may not know, the public safety broadband allocation is the band class 14. It is actually right in here, so we have a, right in here is where we are for our uplink and downlink. The great thing about this, we are actually kind of nestled in here among the carriers. This actually works very well long-term for designing devices so that we can actually leverage technologies, leverage antenna technologies and different things like that, so we can actually have potentially have a device where you could actually roam between the commercial carriers in areas with adequate coverage, and then actually roam onto the national public safety broadband network when those networks start to come online, which there actually is one here in Colorado, if I'm not mistaken.
Yeah, I just wanted to interject real quick. Sure. If you look on the map there, you the band, a spectrum band, you see the downlink. You'll see 763 in the middle there, 763 megahertz. That's the middle of the downlink band, and you'll see that in later RF coverage plots. The uplink is 788 to 798, but remember that 763 megahertz, because we'll be seeing that on.
Rob, that's what you use kind of as your center frequency for all of your mapping. Okay, very good.
All right, well, that's kind of what we just said. Okay, I think we're good to
Yep.
Okay.
Okay, very high level overview of what a basic LTE network looks like. whether it be public safety or a carrier type network. At a very high level, we have our core network at the top, our IP evolved network, where we have links into outside databases, outside networks, and out to the internet, email, different things like that. Transport between our sites and our core network would be our site links. This can occur over fiber optic, it can occur over microwave networks, different types of networks like that. Coming on down to our radio access networks, these are actually our cell sites or our eNode Bs at the tower sites, where we actually have our RF link out to the public safety devices or our user equipment, which you'll see referred to as a UE. That's kind of the common terminology for all those devices out there, whether they be fixed, portable, mobile, different types of things like that. Any questions so far? It's kind of a basic high-level overview of what the network entails. Okay, moving into documenting our users, documenting our user base out there. These are kind of the three things we can use to look at where our user base is going to be. Population centers, as you well know, your user base or your high population centers are kind of in and around just a couple areas. You have lots of rural areas with just 4 to 10 public safety responders that are out in these rural and even some wilderness areas. So we're going to look at some numbers coming up here on some slides and what we can do and how you can look at the different types of network topologies from very high level sites all the way down to micro and femto sites to be able to create coverage where it's going to be needed. Looking at your hazards and your crime, looking at where known areas where there are spikes in crime, where public safety users tend to congregate. One of the things that as Rob will get into with you a little bit later on, is that congestion and the way when users cluster together during large incidents or planned events, anytime public safety entities or our user base congregate together, the way a traditional land mobile radio network addresses that versus LTE network is vastly different. You're gonna see Rob show you some things that how the LTE technology deals with that and how that works.
Just one quick comment on the commercial coverage. So that's a marketing map. So if you go drive test around there and you think you're going to set up like a data bearer and get 3 megabits or 2 megabits, that's marketing information. So that's not information where we went out with scanners and drove test the actual. Sorry for the people on the bridge. I was just making a comment on this slide. The commercial coverage is a marketing map that we pulled from the commercial carriers and aggregated it. So that's not necessarily where you'd be able to even maybe register with the network or set up a data bearer. It's marketing. It's not an engineering coverage map of where you would have received power or some kind of minimum signal to interference plus noise ratio. So just to make that clear.
Okay, public safety's, when public safety is looking at a broadband type of topology or a broadband build out, there's several different areas that we're going to look at to get to our design, to get to our network design. We really want to look at coverage and capacity. These are going to be much different than what we've seen in the past when we are using one of the carriers technologies that are out there. Coverage, of course, this is going to be the thing that's going to be the most critical. Where do we need reliable coverage and for what types of devices? This is going to be much different in a metropolitan or even a suburban area than it would be out in some of the wilderness areas where coverage may only be needed on a very temporary or itinerant basis every several years when we have an incident out there. So we're going to look at some deployable types technologies and things that can be used for those type of incidents and that type of network design. Looking at our capacity. How many total users are we going to have in these areas? These are really going to affect the overall network design, especially when we start looking at site lengths. How big of a pipe are we going to need for a site that might have 10 to 15 users? What happens if we need to send 100 users out there, but on a daily basis we may only have just a few? What types of applications are they using? Video is really, I think as Rob will talk to you about, video is really what's driving the broadband pipe and what the network is really being designed around. the operational area of these users. Where do they travel? How often do they travel outside of their jurisdictions, and what type of services do you wish them to have outside of their normal areas? This takes us to our end game of our network design, or our radio network design, that Rob is going to get in with you and really drill down to the coverage, estimated number of sites, how much is it going to cost, and really what type of parameters are we going to use to collect data on our user base, and what type of applications that they're going to be using. Okay. Rob, where did we get this?
This data was collected from various sources. I mean, we got some in CASM, which is an asset database that OEC ICTAP runs. We also got it from some public sources. A lot of the counties around Colorado, you can go and they have GIS data where you can download some of this data. So it's kind of an aggregation of all this from multiple sources. The point is to kind of illustrate, you know, where are the public safety users, where's the population, you know, where's critical infrastructure, where do we need to focus if we have to prioritize where we put coverage and sites with the objectives of avoiding loss of life or destruction to property or critical infrastructure.
Okay, here's your public safety population report of the, statewide of where your user base is. We got a key here that kind of shows where those users and where those large agencies of 1,000 or more individuals are located. You've just kind of got a scattering of those around these two metro areas here. Other than that, it kind of gets out into, you've got several 250 to 499 areas. These areas are going to require a much more robust and a much higher capacity than a lot of your rural areas, where you may only have, as you can see there, 3 to 49 users, or 3 to 49 individuals inside of those public safety agencies. Over here, we also have a listing of your, by discipline, your law enforcement agencies, how many agencies total, number of sworn officers, sheriff's agencies, state police, so on and so forth. Your fire agencies, as you can see, it's kind of you've got, a good, overwhelming majority of your career. However, there's still a large number of agencies, actually about twice the number of agencies, with a little bit lower number of individuals that are in those volunteer organizations out there. Okay, these are some tools that OEC has available through Public Safety Tools. I'm sure a lot of folks have worked with publicsafetytools.info. The CASM database is available there to all the authorized users. This is a great place to get a starting point for what systems are out there now, getting an idea of points of contacts, folks to start talking to start your data collection process, figure out exactly who is out there and who needs to be a part of the of this broadband network. Number of personnel, what kind of network topologies that they are using, and even what type of access they may have available as far as sites, to start looking at co-location and start looking at different types of partnership type things. Also, we have another tool on the Public Safety Tools site, which is the Mobile Data Survey Tool, or MDST. This is a tool that allows you to you can put this out to entities and allow them to go in and enter all of their agency's information. What wireless carriers they're using today, whether that's personal use, whether that's agency provided, giving you an idea of exactly what these agencies are doing as far as their data use today.
Yeah, just to elaborate, I mean, MDST or something like it could be used as a portal when you want to find out, to help with your capacity design, how many users are out there, how many devices are out there, how many do they expect, how many do they use now, how many in the next 5 years, what type of applications are they using, user profiles, that sort of information, that sort of survey information that you might have to get from people if they don't have applications running on their UE like NetMotion or Radio IP that are constantly tracking their usage as they move around in the course of their job.
Okay, now we're going to end questions. So, questions? Yes.
Early on, you had a slide that shows the evolution mission critical voice. When the LTE network is up and running, will the LMR networks be obsoleted and decommissioned? It's weird that you sort of had a vision that they would continue to be in service.
Do you want to go ahead and say something, or
sure. You know, as a you know, an LMR manager of a system that's been in service for, you know, about 5 years now, I don't think we're going to see the sunset of LMR probably for quite a long time. I just don't think agencies are going to be willing to give that away. They're going to be willing to let that go. A lot of the new public safety, the new generation of public safety responders and focus groups that I've been a part of, you know, the newer generation coming in can see going to, you know, why can't we just do everything with our smartphone? And I think in maybe, you know, 10 to 15, 20 years, we might be able to get there. But I don't foresee LMR sunsetting probably.
So will there be an effort to combine them like the gateways and stuff like that, or will it still just be converge on the user?
I think once voice over LTE and the public safety voice standard is finalized and starts being tested, I think there's going to be an inevitable need for those talk paths to traverse both systems. I think that's going to be inevitable.
Yeah, we didn't put a lot of slides on this, but I have some material I can send later. I anticipate in the next 5 to 10 years you're going to have a lot of LTE LMR integration using gateways, and having people doing push to talk on P25 being able to go through some kind of a gateway or network layer that could be mission critical push to talk to then talk to someone in LTE, because, you know, the mission critical push to talk, even just getting in they started putting in quality of service levels, QCI indicators in the standards in last September. You know, that might not even be commercially available until 2018, 2019. So I think for the next 5 to 10 years, I think voice is going to, voice as an application critical, mission critical voice is going to stay on LMR networks, but there will be that transition time where you're going to have them integrated together.
We use non-mission critical voice over LTE, do you think?
Well, you know, so, you know, the thing about VoLTE is VoLTE kept getting delayed, right? If you talk to a lot of the commercial carriers 5 years ago, you know, they thought VoLTE was going to be out, you know, 2012, 2013, 2014, you know, I mean, T-Mobile's done great with HD voice on HSPA and moving into LTE, but even, you know, Verizon, I'm not trying to pick on any carrier, but Verizon finally got, you know, their rich communication services, their VoLTE integrated with video, you know, out last year, and it was only on like 3 devices. You know, AT&T had launched VoLTE, but it was only in select markets. Sprint still hasn't. Sprint's doing just kind of like circuit switch fallback. So, you know, even getting it to the point where it was commercial grade, quote unquote, you know, took a lot of time. So I don't see it being mission critical grade for quite some time. I think it'll start with push to talk. I think in everyday usage, as long as, you know, potentially information that might not necessarily have to be secured with VPN and all that, you know, could go over commercial VoLTE. But when it's, you know, an emergency event and they need to get that voice call through, you know, I think it's going to be on LMR for quite a while. And there will be, next time we do this, we'll probably put some slides in there showing some more of the LMR LTE convergence. But, you know, if there's interest, I can provide some slides afterwards.
I'm not going to try to take you off track, but with those level of users and that much bandwidth, you can have a lot of excess capacity. Right.
Yeah, we're gonna get into some of those issues a bit later on. Yeah, for sure.
Thanks.
Yeah, excess capacity during non-emergency events, obviously, and then when emergency events happen, then they, you know, with allocation, retention, and priority and preemption, they start kicking off commercial bearers on their actual band class 14 sites. So we'll get into that. I mean, there's a lot of issues that would have to be worked out with roaming on to commercial carriers and what priority they get and that sort of thing. But
my question's more about what do you think about capacity?
Yeah.
Excuse me, folks. Anybody that's addressing or speaking, please be conscious of the nearest microphone and be speaking to it so the folks at the far end can hear you. Better get.
Okay, our next section we're going to move into here. We're going to start looking at some of the network components and what the different radio access network sites look like, based on coverage, based on terrain, and based on where your users are. It's going to take us from you know, from high site, actually deploying an LTE network and a more of a, what a lot of us know as a more traditional land mobile type high site, where those sites are up at very high altitudes, all the way down to a a broadband site that could sit in a router on a desk in a building to provide, additional capacity. So we're going to look at some of those. We're going to look at what all those different types of networks look like. Okay, starting over here, as you can see, as our population density is very high, we're going to start over here with small cells, coverage up to 1 mile. We're going to move into macro cells as we start to get out into suburban areas, moving into rural, to our public safety boomer sites where you can actually have an LTE site that can provide service actually out up to 62 miles is what you can actually have.
Yeah, theoretically, you probably wouldn't design them. I think 10 to 25 miles. I've talked to a lot of RF engineers, and this is kind of what they're thinking for a public safety application. We'll talk about a little with boomer sites, but you can theoretically go out to 100 kilometers or 62 miles, but then you have to worry about the round trip time delay of all UEs being synchronized on the uplink and UEs at the edge of the cell being able to get back to the site. Because there's a thing called a maximum timing advance, which I remember it's about 0.67 milliseconds. And then, and that's a 3GPP standard, Pratch Preamble 3. So it's a longer preamble to allow for that. But you get to the point, how many people realistically are going to be looking at sites 62 miles out? I mean, they're good for experimentation and so forth, but especially when you get into areas that are very varying terrain, you can get lots of shadow effects, and how many sites would actually be built throughout the 62 miles. But the limit right now is based on kind of in simplistic terms, a round trip time delay.
Okay, thank you, Rob, appreciate that. Okay, so boomer sites, 10 to 25 mile coverage. Moving from rural out into wilderness, and here in the state of Colorado, you all are going to have a large area of your coverage footprint is going to be covered by this, somewhere in this boomer to out here into looking at satellite access and backhaul to reach some of those, and possibly even doing off-network or off-net deployable LTE systems that are completely standalone. So we'll look at some of those and what those look like as well when we get out into these wilderness and rural areas where public safety responders do have to travel. Okay, so this HetNet slide kind of shows us how all of this kind of ties together, and the power is really in this evolved packet core, or the EPC, providing site links out to all these different types of network topologies, and this is vastly different than public safety networks that we have today. We do some DAS or BDA type networks in public safety today to drive signal into dense facilities and things like that. However, things like Wi-Fi offloading and being able to do some of these small cell technologies all kind of wrapped into one and connected into this overall packet core is much different than the way we do things today.
Yeah, I think with the public safety network, if you're assuming it's all band class 14, you would be on the same frequency. But in the commercial world, these are multi-band, multi-radio access technology networks. And this is kind of a simplistic drawing, but you could have a situation where you're in a dense urban area and you go into a building and you could get on an indoor E-node B, you could walk out of that building, you could be on a small cell that's trying to push a lot of capacity in a very small area. And then you could have an umbrella site above that, which could be a macro cell. And we'll get into it a little bit, there's a lot of issues of turning macro cells off and small cells on and off so they don't interfere with each other. It's a little bit easier when you have different frequency bands to keep them kind of separate in frequency. You're dealing with one frequency band and you've got one 10 megahertz channel. It gets a lot more tricky with interference. You can have a macro cell stomping on a small cell because the transmit power is much higher. So, don't look at this as an architecture slide or a topology slide. This is just kind of listing some of the different types of network infrastructure components or methods that you could access an LTE public safety broadband network. And obviously with Wi-Fi offloading, that for public safety that might not be appropriate because it's in an unlicensed band and it's not really a reliable RF medium that you want to necessarily be using. But the commercial world uses a lot of these. When the commercial world built out LTE, they did release 8. The last year they've been doing release 10, which is advanced LTE, which some people would argue is 4G or not. Now they're going to be looking at massive deployment of small cells on an order of magnitude much larger than the macro cells that are out there to try to boost up the capacity and really push the RF coverage and capacity and the signal to interference to noise ratio distribution where it's needed based on where their customers are.
Okay, macro cells. This is really our standard type of deployment for a suburban or even into a metro area. This is your 1 to 8, I would say 1 to 8 to 10 mile coverage sites. Here looking at macro cells, these are your typical, 200 to 150 to 200 foot sites that you're going to see. And this map that you've got here, are you interested in coverage of what some of those sites look like?
Yeah, and these are kind of the basic building block. You start building a design. You want to go for coverage first. You use macro cells. You cover the cities. You cover the highways connecting them. You cover the major areas where you expect most of the in the commercial world, most of the population to be. In the public safety world, you look at it for coverage. Where would you want to have it to prevent loss of life?
Okay, commercial sites. This is a map of all of the available commercial sites within the state of Colorado. Down here at the bottom, we've got a key that shows some of the owners of some of those sites. LMR commercial sites that are potentially, those are all public safety sites, as well as railroad, and then some of the site development organizations are also shown there. Okay, as Rob mentioned, this is your advertised coverage for 2, 3, and 4G cellular as it stands today in the state. Again, this is what's advertised by the carriers. We've
marketing maps, yeah.
Aggregated all that together. Marketing maps that you see out there. Of course, what you may get inside of buildings and other challenges to propagation really aren't shown very adequately on these types of maps. This is your state LTE cellular coverage as it stands today.
It might be a little bit out of date. They might have a little bit more expansive coverage at this point, but.
Okay, we're going to talk about roaming for a minute, and this is going to allow, or potentially allow, let's say we have a band class 14 device, and we may have several sites that are in service. However, we're going to need service, or we're going to need to be able to traverse this highway area. So we feel it's going to be critical for the initial rollout of these band 14 devices to be able to have the ability to roam over onto the carriers that also have a comparable or a compatible band. So where the map that we showed earlier that showed the other carriers kind of surrounding the National Public Safety Broadband allocation at 700 megahertz, having this device to be able to reach out to those other networks and be able to fill in that coverage. So for instance, we have a particular site here that does not have band class 14. We have another site here that may not have band class 14, and then we get into an area where we might have some band class 14 sites deployed, and macro cells deployed. So as this unit traverses this area, his devices or his or her devices that they have along are going to be able to basically once they reach the edge of the sector for that band class 14 site, the device would auto roam over to the respective carrier that your organization may have an agreement with. Of course, this is going to require roaming agreements between those different networks, and to have devices that would be able to be recognized on multiple bands, multiple radio frequency bands. Anything else you want to add on that?
I think it's good. This could be the scenario where you want to have a lot of coverage right away, but you haven't had time to install all the band class 14 on a subset of potentially commercial sites you might have a spectrum and infrastructure sharing relationship with. So you could roam on their sites as you're building out band class 14 sites. But for the ultimate quality of experience of the user moving between different cell sites, some of which may be, let's call public safety sites with band class 14 and some which might not, you want to have those roaming agreements in place, and also some kind of IP tunneling and relationships to pass priority parameters between the two. And that has to do with, the partner you have, what are they willing to let public safety users do? Are they willing to let public safety users come on and make use of some of these priority mechanisms? Are they willing to rip off default bears of their commercial customers and let public safety users have them, or voice VoLTE bears that commercial users are using? I mean, that would all have to be worked out.
Those roaming agreements are for individual carriers, for individual agencies? Or is it something that could be broader to more of a consortium that is?
Well, for everything, obviously, it would be better for cost and, easier to work off one service level agreement and that sort of thing, one contract. I would say a big of a consortium as you can get together with, one or more carriers, because that'll give your roaming partner more potential users. You can offer potentially more spectrum in more places. So yeah, definitely the more the better in this case.
Okay, co-locating band 14 equipment in existing sites. This is going to require a new antenna array for band class 14.
Yeah, maybe not in all cases, but the funny thing is there could be carriers out there that spent a lot of time in the past actually trying to reject interference from the band that we may be using, so they might not have antennas exactly optimized to use band class 14.
Okay, so upgrading existing eNode B equipment to add band class 14 carriers, that will be possible with a lot of the new networks that are going in today. And even looking at co-locating that equipment or those nodes inside existing equipment shelters, or adding new enclosures at existing sites. Adding microwave antennas, different types of things that are going to have to be added for backhaul or bringing fiber into the site. And here's some bullet points here on some best case practices for adding LTE to existing commercial sites. Best RF coverage based on capacity without interference. Structure height, as far as looking at heights available for new antennas to be added to the site. Backhaul is going to be of course preferably fiber backhaul back to the EPC network, back at the network level, at the high level. Existing tower loading and site hardening is going to be a big one, because as we know today, the carriers' standards for sites aren't necessarily at the same level as public safety. They have a different model that they're looking at. So if we're going to be adding and moving, as we move away from LMR, or we start moving toward mission critical services running across band class 14, if we are going to be using commercial sites, we're going to need to be sure that those sites are hardened up to at least our current level of standards today. Being able to have battery backup time at the site, being able to have backup power generators at the site, and any other hardening standards that you may require depending on where your sites are located.
Yeah, and there's a document by NIPSTIC that actually has a lot of good recommendations for site hardening of sites. So.
Who's that?
NIPSTIC, NP, what is it? NASA. Yeah. There's a doc.
NIPSTIC has a good working group and a nice set of best.
Oh, that's the last bullet on there.
Yeah, you're right.
I thought that was somewhere.
Yeah, you're getting close there. So public safety grade site hardening of those commercial sites is going to be key. Physical resiliency, operational resiliency, being able to be sure that we can access those sites and that we have them protected as well as possible against wind, water, ice, different things like that.
Okay, good.
Okay, looking at our commercial carrier cell systems, some of the pros and cons, and we're going to have several slides that kind of do this back and forth to show you some of the pros and cons of some different types of network topology. Some of the pros, the commercial carriers, they already have over 250 sites available throughout the U.S. They have extensive backhaul systems, and being that they are already into the broadband or already into the LTE business here for several years, they have already built extensive backhaul networks that have a lot of capacity on them, and they already routinely share sites with one another. Some of the cons is going to be these sites are, again, as we discussed already, may not necessarily be public safety grade. They may be not necessarily built up to our standard of what we expect and what we have strived to provide at our public safety LMR sites. Again, these sites are going to be geared toward public subscribers. They're geared toward a profit model, and that doesn't always necessarily mesh with what we are looking to provide. They're looking for maximum data throughput, where public safety, we really need coverage and reliability are our main two key points. Some alternatives, we may just want to share real estate. We may be able to co-locate with some of the commercial carriers going forward with our LTE deployments. Sharing infrastructure, looking at towers, and maybe even perhaps looking at long-term agreements that you were talking about, being able to not only share the RF piece of it, but maybe we can even look at sharing backhaul or sharing fiber or microwave networks to be able to make those systems work together.
Yeah, one thing I think we forgot to put on here is that, you know, in Europe, it's a lot more common to see a lot more sharing of backhaul and a lot more of even sometimes even seen equipment shelters, which is pretty shocking. Usually in the States, you go to a site, their carriers are kind of in different equipment shelters. They might be sharing fiber if there's a company that's run fiber there and they're selling backhaul capacity. But, you know, one of the cons too is when you get in a situation where you're at a site where there's a backhaul provider, there's a tower company, there's multiple carriers, and you know, if something goes wrong and you've got you know, who do you have that SLA with for system availability end to end? You know, the fiber provider say, oh, it wasn't us. The microwave guy goes, it wasn't us. It was the you know, the tower company. Or so there are more people to point fingers at. The more entities you do get involved in this when you start sharing everything, backhaul, tower, all the infrastructure. So.
Okay, moving into starting to look at our public safety sites. These are existing public safety sites that were pulled based on FCC.
I think this was pulled on FCC or some CASM. Kim was nice enough to give us, for the 3 counties, we're looking at a lot more sites. So we did get quite a few more sites for the 3 counties that we looked at.
Okay, so moving into looking at leveraging our public safety LMR assets, or using some of our existing sites going forward, looking at the broadband deployment. We already have accepted standards. We're already at the P25 level, looking at things like R56 and different types of site specifications that a lot of organizations and a lot of us, when we put RFPs out for sites, building new sites, we're already building to that level. So we're already at that hardened site level as far as our wind and ice loading. That's a big concern out here. Emergency power, site security. Those types of things that we look at from a different perspective than a lot of the carriers do. Direct mode fallback. This is something that actually is being talked about right now with 3GPP. How are we going to be able to do off-network communications if we have a group of people going way out or far away from where the network is? Today we select you know, simplex frequencies that we all have that are in the NIFOG manual or whatever the case may be, statewide or regional shared channels that we might already have in place. How are we going to make a broadband UE device talk to another broadband UE device on some type of off-network capability? So, especially when those devices currently are in the, you know, probably 250 to 500 milliwatt maximum range as far as their transmit power output, without external antennas or, you know, with built-in internal antennas and things. So that direct mode fallback is going to be a big piece, and then interoperability emphasis. These are things we're already doing today. Looking at some of the cons, site spacing may not necessarily match for LTE requirements. We may not be able to necessarily add you know, these sector panel antennas for LTE, for an LTE macro or a high site or a boomer site, which we'll look at shortly. That may not be able to coexist with our existing LMR network that's out there. In a lot of cases, we aren't going to have adequate backhaul. The way that we've done backhaul and the way we've done site links for LMR is much different and much lesser capacity and different style than what is required for LTE. So we're looking at going from circuit switch type networks over to you know, packet switch, and having a large site pipe to be able to reach back into that core. Okay, small cells and Wi-Fi. Now we're getting down into you know, where we're going to be providing coverage for a very small area. So we've looked at the typical macro cells. Now we're going to look at some small cells and some areas where those would likely be needed. And in fact, there was a network of small cells set up out in Vail here recently for for a test bed project that was going on out there. Some of you may have actually been a part of seeing that operate. So these small cells are typically for coverage for areas of 1 mile or less, or maybe even smaller, maybe even just several hundred yards, where there's going to be a large congregation of public safety users that may be coming in for a special event. This may be a headquarters facility, a training facility, or maybe even a deployable system that you can take out and connect back into that network. So these are just some areas I think that Rob identified as areas where small cells and Wi-Fi offloading would be ideal in some of these high population density areas.
Yeah, there's a little bit of overlap, I think, between small cells and deployables. So, deployables, we'll talk about it, but that can be used to bring coverage to areas that don't have coverage or inject temporary capacity in areas. What we're trying to illustrate here with the small cells is they're really used by commercial carriers, and they'll probably be used, once a public safety LTE network's built and it's using macro cells for coverage, they'll have UE metrics, and they'll start collecting, and they'll start finding out where they might have capacity problems, and you start what they call infilling areas that already have coverage, but you need additional sites to provide more capacity, because ultimately the entire capacity you offer from a network is a function of the bandwidth you have, which is 10 megahertz up and 10 megahertz down, the cell spectral efficiency of each cell site you have, and the number of cells you have. So if you've maxed out the cell spectral efficiency, you've placed sites where they're the most optimal place you can place them. You obviously, unless you get more frequency besides the 10 megahertz up and down in band class 14, you're pretty much got to start adding sites if you want to increase overall network capacity. So what we're trying to show here is, in urban areas or areas like Vail, where you get massive influx of temporary population above the normal population, you're just trying to bring in smaller cells covering a smaller area to provide more capacity in that area. Which maybe we already said all this.
Yeah, pretty much. Our small cells are typically going to be 100 milliwatts to typically maybe a 5-watt device. These are devices that we know today. Some of you probably even have one, which is kind of a home or office gateway that may link back into your cellular carrier that the cellular carriers provide. It's going to be a very similar type device that could be it could have a small Ethernet pipe back to the evolved packet core to bring that coverage down to a very small bubble where you may need to have coverage. This could be inside. These can actually be deployable as well. You could take one of these with a satellite node and be able to provide a bubble of coverage. So as Rob mentioned, deployables and small cells kind of overlap at certain points, and we will talk about that a little bit more coming up here. These can support up to 100 users. Some of the issues with these that you may have experienced if you've ever used one of those little small gateway type devices is handoffs between the macro network and those micro networks don't always happen very seamlessly. We can actually see interference between these micro sites in bands 13, 14, and P25. Those bands are very close together, and typically the carriers have had lots of different places where they can stick that stuff. But we're going to be working with 2 blocks of 10 megahertz right next to each other. Okay.
Yeah, so just a couple more points. I mean, obviously, when you start adding a lot of cells, I mean, if you add a small cell and you're adding it for capacity, well, you need backhaul, right? So backhaul is always a problem with small cells if they're on light posts. It may be very difficult to put a microwave dish on it because the light post moves a lot and it'll go outside the 3 dB beam width of a microwave shot, especially if you're trying to use a microwave frequency that's very high, even up to a millimeter wave like 90 or 70 gigahertz. This is like pencil beam width. I've aligned some of these links, even aligning them at a half mile. It's very difficult to do. Also powering it, and also physical security. I mean, if you're going to put these small cell E-node Bs on very small structures, I mean, people can climb them, they can tamper with them. There's network security issues, there's physical security issues, also timing. If they're in a concrete canyon in a street and the buildings are very tight together and they can't get a GPS signal, and you need to have precise timing because you've got a lot of synchronization in LTE, you need a timing source. Well, if you want to do like an IEEE 1588 precision timing protocol, or you need 0.5 microseconds or something for your timing, that's very expensive to put that equipment in. So you need NEMA enclosures, interoperability between all these different types of cells. We'll touch a little bit later on about what's coming with what people are saying is coming with 5G. It's just more of what you see now. It's even smaller cells. You could have 3 or 4 cells in this room made of a thin type of paper material for an antenna just covering this room. I mean, it's going to be trying to blanket coverage and capacity everywhere. All those issues become very problematic as if you got users moving across multiple. Now, again, you're on one frequency band, but if you've got a roaming agreement with a commercial user, you're moving across multiple different cell types, across multiple different frequencies. Trying to keep that quality of experience can be very hard. Certainly with one, in one frequency band, the upper 700 megahertz band and 10 megahertz channel, if you've got small cells and macro cells you're constantly pinging between, you have a lot of potential for interference, and you have to have the ability potentially to even turn the small cells on and off when you need them remotely. And they're more ideal also for lower mobility and pedestrian traffic. I might get into this a little bit later, but when you have small cells in an urban area and you start looking at different what they call channel models of pedestrian or vehicular or even up to train, you can get Doppler shifts of up to 300 hertz with these, and it's very hard to control your signal to interference to noise ratio, which we will beat to death a little bit later on in this presentation with small cells. So they can be very helpful, but the engineering and complication of interoperability when you start introducing small cells, it goes up exponentially. The good thing about there's a lot of work being done in 3GPP looking at small cells, even potentially increasing the modulation scheme up to 256 QAM for them. The current limit with macro cell, well, the current limit LTE 64 QAM. So there's a lot of interesting things being done, but there is a lot of, I don't want to just say small cells, you just go dump them in your current design and they're fine. There's a lot of interoperability issues to deal with. Oh, and one more point, sorry, I want to make. If one of my friends who works for a small cell vendor said, can support up to 100 users, you'd be like, no, you're not right. We can do 400, 600 users. Okay, they can sell you more expensive, the OEM can sell you more expensive modems and equipment to increase your number of users. The 100 is just kind of a generic term. You can go up higher than that. You just have to, again, the whole point with small cells is to not spend a lot of money and bring in a lot of capacity, and you start having a very expensive modem, all this physical security, all this interoperability timing, you start making the site very expensive. Which I think we just went, did we go over all of it?
Pretty much did, yeah. Okay, so small cells, pros and cons. These are great for tactical use to increase capacity in high demand areas that may have a surge of users during certain times, whether it be an incident or an event. These can be deployed. Typically, these are going to be lower cost than putting in a macro cell. And we can reuse our existing spectrum. Rob talked quite a bit here about some of these other issues. These can be tampered with. These aren't necessarily going to be able to be secure the same as a typical macro cell would. Backhaul and power availability is always a big concern, especially when you're talking about DAS networks and things inside of buildings. You know, what happens when the power gets shut off to the building and you lose coverage, different things like that. Limited number of users, and there are those interoperability and network management pieces that Rob covered for us as well.
Yeah, and the timing, there's even small cells that now are starting to deploy something called MIMO, which is multiple input, multiple output. And what that is an antenna processing system that you can put at sites where if your user device is in what I'll call a sweet spot distance away from the cell site and you have a lot of diffraction and multipath fading going on, you can actually have two different you can do spatial multiplexing and get two different spatial pipes coming to that UE, and you can make use of diffraction and time delay, and actually you can increase your capacity. So that timing issue and also the maximizing your signal to interference to noise ratio issue even goes up more when you start introducing MIMO technology to small cells. If you guys, some of you were here in July in the last presentation we did, you know, we went into MIMO, and if we have some time, we can talk about it later.
Okay, we're going to move into we're going to look at high sites and boomer cells. This is going to be probably the biggest difference in between what the carriers are doing today. That is something that could be a possible deployment technology for public safety broadband. This is going to be key out in areas where it's going to be a little bit more rural. Getting into those rural areas, being able to cover, you know, a 25-mile or maybe even a further radius away from that site, using tall towers, using geography, mountaintops, and things like that are going to be very advantageous to cover these large, expansive areas where we can have one site cover those organizations that may be down in that 3 to 50 individual agencies as far as the first responder population goes. So we'll look here at high sites. Up again, as Rob mentioned, up to 62 miles. That's a theoretical maximum of the technology. You're probably going to see more like what you said, 10 to 25 miles.
Yeah. One key point too, I think, want to make, maybe we'll just go back here, is as we're decreasing the population density, we're getting into the area where the commercial guys might not have a footprint, so the ability to use a subset of their sites starts to go away. So this is where you could start leveraging your existing LMR sites that are very tall sites or are on very tall terrain points.
Okay, very tall structures, very high above ground level, tall mountaintops, tall towers. This would be, as Rob mentioned, a very good use of to be able to reuse existing LMR mountaintop sites or those high altitude sites that you may already have. This is going to, of course, if you're having a tall tower, going to require the use of tower top amplifiers and/or remote radio heads to actually remote the nodes up to the top of the tower, which is actually becoming pretty commonplace in the commercial world now. Power and backhaul issues, of course, are going to be a concern for any of you that are operating high sites and remote sites today. As you know, certain times of the year, access is a problem. I heard some guys talking about snowcats earlier for accessing mountaintops and things like that. Those are things that are going to have to be taken into consideration, as well as being able to drive test and optimize those sites and dealing with any kind of shadowing, which Rob will cover with you coming up here when we start really diving into coverage. Looking at, you have a much higher potential with that high site to have shadowing or coverage issues, when you get out to areas where the geography or the terrain may change. This does reduce the overall cost. One site can cover a much larger area and not having to have near as many sites. So we've actually got 3 different types of boomer sites here. We have, a fixed site. We also have a host or a capacity donor site, which we can actually use as a relay. So we can actually use that to relay out to, I think you said 1 other site or 2 other sites, depending.
Yeah, I mean, you have to keep in mind that I was going to say your chip rate. I'm getting back to CDMA, but when you start, the whole point with these. Sorry for this car moving. I'm getting like a seizure looking at this thing. I got to check the animation on these better. If you have a host capacity donor site, that's providing capacity, say like on a highway where you need it, but you might have to go off the highway in a more remote area, and you could use something which is a LTE relay node. It's basically kind of like an active repeater. It's not increasing your capacity. So what you're doing is you're sitting on a highway and say you've got line of sight, or at least you can get using the in-band LTE 700 megahertz band class 14, you can reach a site 4 or 5 miles away. You can put up a site that's not going to increase capacity. It's just pushing coverage out farther. So if you had a UE and that police car down there under the coverage of that relay node, that UE is basically going to think it's attached to that host capacity donor E node B site. That relay is almost invisible. Now, you could talk about using relays. The good thing about relays is that they'll reduce the cost, because you could have just E node B equipment, forget antennas and all that. Just the equipment could be $50,000, $75,000, and if you could replace that with something that's a third of that cost, that's extending coverage, that's great. Now, what plays into this is if you have a partner that you're giving some of this excess capacity to, they might not be too thrilled with a relay node. They might want capacity there. So using relays is going to be, a decision between public safety needing extra coverage and not spending so much money on the infrastructure versus what are the capacity requirements of your infrastructure sharing partner, if you have one that would like access to that excess spectrum. One other point we didn't put on here, which we should, Jason had mentioned that the commercial LTE UEs right now are power class 3. They're 23 dBm, so they're pretty small power compared to public safety. There is a power class 1 that's got in the standards, I think in 3GPP release 11, that goes up to about 31 dBm, potentially 33. So it's getting up over 1 watt. So having a handset like that in this remote area would help a lot to try to extend the range of that boomer site. Of course, then the issue is, you know, how many device manufacturers are going to build Power Class 1 handsets? What's the demand for them? You know, and how expensive would they be? But it could help extend some of the coverage area in these boomer sites.
Okay, some pros and cons of high sites, extenders, and boomer cells. We can get wide area, 10 mile. We can get those wide area of coverage to exceed 10 miles up to 25 miles. Of course, those do require those tall sites and or high terrain geographic features to be able to create those. That is one thing that in public safety, especially here in Colorado, there probably is a significant amount of those in certain areas of the state where you do have those assets to leverage to offer up when the deployment takes place. This can obviously bring down your deployment costs in areas that have lower population density, where you're just looking to extend coverage out to those rural areas where there may not be the ability to partner with carriers, as Rob was talking about. There is high probability for line of sight due to that height, and this would be a great support site for those deployables and relay nodes, and we're going to talk about deployables here coming up next. Shadowing and coverage holes can be created with these high sites to much more of an extent than a standard macro cell would. And getting backhaul and power into those remote locations is going to be much more challenging.
As far as the boomer sites or the high sites in general, considering Colorado's terrain and the likelihood really that we're going to have to utilize these, I understand that this is a technology that really does not have a lot of research behind it. It's 3GPP has not really put much into it. I don't think the cell companies really care much about boomer sites. And you've mentioned a lot of the limitations, such as like the UE, the low power UEs, obviously that's a limitation. But I think a lot of us in this room, and probably in the radio community in Colorado in general, have a lot of experience with high sites, mountaintop sites, and 700, 800 propagation. So we know it works. Right. In a narrowband environment, it works, and it works quite well.
Right.
When you bring in the self-interfering network of an LTE 10 megahertz bandwidth, what sort of limitations do you get into when you start putting these high-power sites up high on mountains that potentially can extend, let's say, up to 50 miles, whether they'll be usable at 50 miles?
Right, right. Well, there's a slide that talks a little bit about that, about the dominant server problem, where you've got, you could have terrain shadowing where you're in a vehicle and you're actually very close to a site, but you've got a little bit of terrain blocking you from that, and if your RF design wasn't very good and you didn't use very small terrain bins, like below 5 meters or something, you might think that's your best server. What's actually happening is what actually your best server is actually a boomer site sitting that could be 20 miles away that has line of sight to you, that is blowing off, that is causing a lot of what we'll call a signal to interference to noise ratio, which we'll get into, because it's interfering with it and it's kind of destroying that predicted SINAR that you had, assuming that closer site was going to be your best server when actually your boomer site is. So yeah, certainly there's a lot of experience in that frequency band with narrowband, but because what we're doing is so, because everyone's interfering with everyone else, because it's a, you know, LTE, we didn't mention it before, it's a frequency reuse of one. So every sector on every site, everyone's using that same 10 megahertz, trying to use it in the same time transmission interval at the same time. So you have to very much control SINAR. So you're right. You might have a boomer site that works now for LMR, you know, out to 20, 30, 40, maybe even, I mean, you would know better than me, but once you get out to about 20 miles, that thing may only be usable for your capacity and coverage needs out to 20 miles, but it's still blowing off other cell sites. And that's why I make the point, it's so critical to do drive testing and figure out exactly where that coverage is. And you're right, there is not a lot, because the commercial carriers don't focus a lot on rural. You know, they haven't done a lot of testing like this. I know at the Public Safety Communications Research Conference in June last year, you know, there was a guy who had done, I think he did it up to 45 miles or something, you know, and if I remember, it was fairly flat terrain. I can't remember where he did it, if it was mountainous or it was more like the eastern.
It was just straight up by 25.
Okay.
I'm not positive,
Yeah.
but I think it was also done in the absence of other interfering sites.
Right. So it was, right. So he had probably a clean, so he had, so great for determining the morphology effects. If he actually used an LTE signal and he used an LTE scanner, he had something no one ever gets, which is a completely clean channel, no one interfering with you. So you can actually go see what that, and do actually really good measurements on the morphology to tune your RF modeling tool. But yeah, it would not be the actual experience you would have when you start lighting up sites around there and your SINAR starts going down because everyone is interfering with you potentially. So yeah, no, it's a great point, and it is going to be much harder to use those boomer sites and optimize them than it was using them for LMR. One, because you're putting much higher capacity, higher modulation schemes, and also because of the signal to interference to noise issue that really is the controlling factor in the LTE designs.
Just one brief follow-on question. Has there been any discussion about catenating the spectrum, splitting the spectrum off to, it's sort of in a quasi-LMR environment, sort of like we do now, where you have some staggered frequency reuse to alleviate that. So 5 by 5 here on the bottom end of the band, 5 by 5 here on the upper end of the band. They can cross each other all they want. They're not going to interfere.
There's a source that I put in one of the slides of the Fujitsu paper that's available on the internet, and I would pull that down and read it because it gets into a lot of what you're talking about. You've got this interface between eNode Bs called the X2 interface, which is supposed to do a lot of interference control, and there's a lot of talk about, and I'm not sure how many carriers are actually doing it, is in doing interference control. See, the problem is with the frequency reuse of one, when you're at the cell edge and you're looking at a cell site and you're exhausting all the resources of that sector. Say the sector can do up to 55 megabits, we'll say some theoretical number, but you're really seeing 3 megabits because you're right at the cell edge and that's what you designed the cell edge experience to be. You're using 100% of those resources. When you calculate SINAR, you're assuming that all the neighbor cells around you are at 50% loading. So what happens is if you start really loading up and everyone goes to 100%, everyone gets blown off the air at the cell edges because you've got users trying to use the same subcarriers at the edges of different cells. So what people are talking about is kind of what you're talking about in terms of slicing off the spectrum, slicing off a third of the bandwidth or subcarriers to say, okay, if you're at the edge of the cell, you can only use this 1/3 of the subcarriers. If you're closer into the cell, you can use more, but we're really worried about interference at the edge of the cell and destroying our SINAR. But if you look at the source will be up there. If you look at that Fujitsu paper, it has a lot of interesting ideas of how you solve a lot of this interference that affects handover distances and overlapping between cell sites, how to maximize your SINAR by doing this kind of reservation of certain subcarriers at the edge of the cell and only allowing those to be used at the edge of the cell to kind of combat. Yeah, there are techniques to compete at both in power and with use of certain subcarriers, but that's a lot of simulation and a lot of white papers, right? Who's gone out there and actually done it? I don't know anyone who's done it for this kind of for boomer sites.
11,000 people.
Right. No, yeah, you're absolutely right. So what you would do is you do your initial prediction of your SINAR and you try to use that site, and then what you do is you've got some kind of automatic cell planning module in your RF tool, and you'll have to really, and you need very precise terrain bins and morphology to do this, to down tilt a lot of the, you're going to have to down tilt those antennas on those boomer sites so that they're still providing the coverage you need and your cell edge minimum throughput, but they're not blowing off other sites around them. So it's a really complicated topic to talk about, but then in general, I hope it kind of answered the question. But if you read that Fujitsu paper, it goes into, not for boomer sites, but it goes into a lot of those interference issues that you will see when you have dominant server boomer sites. So what that's supposed to show is deployables everywhere. I don't know, my circle, I guess, isn't very visible. It's supposed to show them everywhere.
So now we're out into wilderness, we're very rural and wilderness areas where we're actually moving into talking about deployables or bringing your network with you when you go. This is a not necessarily new. Land Mobile has been doing this for a number of years now. There's most regions now have sites on wheels available to them. Networks on wheels that you can bring in to stand up a bubble of coverage in a particular area where you may need it. This would be particularly effective out in your rural and wilderness areas. So we'll move on to the next slide here and talk a little bit about what.
Wow, what happened there? Ooh, that's bad.
Okay, so I'm going to get my picture.
Yeah, sorry, I don't know what happened. They got looks like they got merged in. Must be too. Sorry. Well, sorry.
It's good on here. So
did the people on the bridge get the PDF file? Or,
I didn't send it out yet.
Okay, sorry. Okay, sorry for people on the bridge. Yeah, there's some text is sitting over each other, so.
Okay, so LTE deployables, I'm going to have Rob kind of talk us through this block diagram, but I'll briefly talk about the deployables and kind of what they're for. Our fundamental elements for a deployable LTE platform is to be able to have an onboard evolved packet core, or basically bring the entire network along with us, along with the RF node or the E node D, to be able to mobilize a network out in a rural area or a wilderness area. This would include meshing, having a mesh capability and a self-organizing network to where 2 or 3 of those nodes that you might stand up would be able to talk to each other over a sub-signaling bandwidth to be able to form a mesh network out there on their own. There are form factors, subsets of this technology that have been reduced down in size to be able to fit into vehicles such as a Humvee, such as a police car, a command vehicle, to be able to have those networks taken out with us. We also have the ability to set those up in a man-pack type of environment. And I believe some of the defense technologies and things that the military is going to kind of spill over into that capability, so where we could have a man-pack deployable E-node to be able to carry out with us to provide coverage, even to include having aerial coverage to be able to have an unmanned vehicle or other type of aerial asset to be able to provide a node for a particular area. This is really scalable depending on the size of the mission.
Yeah,
Rob,
I just want to add, so, we show this evolved packet core in a RAN and a tower fitting in a Humvee, and you say, well, how do you do that? Well, a lot of the vendors that have these deployables, they've taken the LTE protocol stack for the evolved packet core, and they run it as a Linux application. So it basically could sit as a software program on a very small server and run. And the evolved packet core, we're not really going to go into it in this workshop, but a lot of the mobility management entity, the serving gateway, packet gateway, PCRF, they can be separate physical boxes. They can be one physical box, depending on what your architecture of your core network is, if it's centralized versus distributed. They can be run on virtual machines. You can run them on, HP servers if you want. So what the man-pack really, get down to a man-pack, it's really like a small E-node B radio, and it's got a processor and a server in there that's running the LTE evolved packet core protocol stack. And you say, well, why would you want to do that? Well, if you're in a deployable situation and you lose coverage with the main network, you still want to have functions like your PCRF and all that to do priority. You might have a Humvee that has a, well, actually, we'll talk about it when we get to a later slide. I think it illustrates it better.
Okay, so some of the characteristics of these deployable networks, or some of the reasons we might put these out. Surge capacity would certainly be a large one for planned events. Any place that we're going to have an incident or a planned event where we have determined there's going to be a large grouping or a large gathering of public safety users, or those UEs that may congregate into one area and overwhelm that macro site coverage. This is when we would probably bring those in. Backhaul is going to be necessary to make those work, or to be able to link those back into the overall EPC. So fiber or microwave capability is going to have to exist there to be able to get that coverage back into the network. Remote coverage also. This is where we would be basically, as we were talking about, bringing your coverage with you. And backhaul in that situation or that scenario would be likely have to be over SATCOM or through microwave capability as well. We most likely would not have fiber capability in a remote area such as a wildfire or a missing person search or something like that. Okay, this is basically kind of how deployables get plugged into the overall picture. We have some deployable resources out here on the edge of the network, providing coverage out into a rural area. We have users that are interacting with those microcell or those ground vehicles. Those networks are actually, you can see actually there's several potentials for linking back in. We have a microwave backhaul to be able to go back to an adjoining microcell that may have some microwave capabilities already on it that we could point back to. We also have satellite backhaul as necessary. as well as we're interacting with some UAVs here that may also be talking back to, or they could act as a relay. As Rob discussed earlier, actually having the next closest out macro site could act as a relay to provide that service out to those deployables, and then basically being able to backhaul those networks and backhaul those applications back all the way back into the Evolved Packet Core and back to all the way back to a PSAP, conceivably.
A couple of questions about that. First of all, what's the maximum speed at which a vehicle, or in this case a UAV, can be traveling before Doppler becomes an issue?
Yeah, very, very good question. Yeah, I forget to put that on there. Yeah. So we're kind of assuming that, that Humvee there is probably parked and stationary, kind of somewhere near where a forest fire might be happening. And then the fighters are going out and they're meshed back to that. And that's kind of the backhaul point, whether it's satellite or microwave. And I view these platforms in general as kind of static. What's in the, I guess, kind of pink or mauve kind of circle there. And then it moves as you're moving with whatever issue you're trying to deal with. The UAVs obviously have to go fairly slow. They ideally would like to keep line of sight or within a range of, a mile or two up or away from that Humvee. And hopefully that Humvee can park in a place where it's not behind trees and it's got some decent line of sight. Or if it's behind trees, they're not too thick and the 700 megahertz can get through there. But yeah, the UAVs, the issue with them is how fast they go and how long they can be powered for. Can they actually remain airborne as kind of an aerial active repeater back to your terrestrial network for hours at a time? And also they would have to have omni antennas or some kind of very complicated pointing angle mechanism for the antenna to try to maintain pointing or direction towards that Humvee. So this is a very kind of simplistic, a little bit of a hokey drawing. What it's trying to show is there's a lot of different ways you can get backhaul and you can attach back to the terrestrial network with deployables. Now, if you've got an Ethernet microwave shot, if you're lucky enough and have line of sight, which when I was at Nextel and I was talking to the guys that we went out and would do NASCAR racetrack, we never had that. We were always, we'll bring the microwave, but we never used it. It's always like back on satellite, right? So you usually get a couple of megabits. So the thing to realize here is you may have a deployable eNode B that can do, let's say, up to maybe 33 megabits per sector, theoretically 50 or something like that. But then you're on a backhaul of a couple of megabits, and you also have latency with the satellite backhaul. You want to keep about, 50 milliseconds, something that you don't want to go beyond too much of that for your UE that has to go all the way back to your core network if you have to, download data from a server or something like that. So there's a lot of issues here. There's, what backhaul do you have? Can you do an aerial active repeater with UAVs? How fast are you moving? As long as you're moving at kind of pedestrian or vehicle somewhere between maybe 5 or 70 hertz of Doppler shift, you should be okay. The good thing about the meshing is, if it's a self-organizing network, it can take one. It's almost like a MAN-A, like a mobile ad hoc network. It can take one user kind of falling out of the mesh, and it'll kind of self-heal, so that you don't have any kind of single point of failure. Obviously, if the Humvee blows up or loses its backhaul, then you get cut off from the network. But you could still be able to talk amongst yourself in kind of a walled garden scenario. But you're absolutely right. This is making a lot of assumptions about spatial relationships and time with these pieces moving between each other. And one of the projects I would like to get off the ground is somehow hooking an RF modeling tool in with a network management system that could actually determine at the Humvee where the RF coverage is the best and could actually direct users or signal them when they start moving out of that pink circle and say, hey, look, you're moving out of coverage and capacity. You're running an application now that's very high capacity. You're going to get throttled back. You could get pixelation in your video. Or we lost our microwave backhaul. Now we're on satellite backhaul. Any application you're doing that's extremely latency sensitive is going to start falling apart. And I don't know anyone's really done that. It's kind of one of those, nirvana things you'd like to see. But yeah, thanks for bringing up that point. I always forget to mention that.
You mentioned the sensitivity of the RAM to latency, and I think you said about 2/3 of a millisecond is sort of max tolerance.
There's, over-the-air interface, you want you would like to see microseconds or 5 milliseconds, and it depends on the application you're doing. I don't want to throw out a number that works for every single application, but yeah, kind of the order of magnitude, yeah.
Assuming that, how does that transfer out to the backhaul? Is the backhaul also that sensitive to that latency, or is that just on the radio access network? Because 2/3 of a millisecond, I mean, that seems like satellite links are going to just blow through that.
Right, yeah, satellite, right.
On the order of 640 milliseconds.
Right, exactly. So when you start getting over 300 milliseconds, you know, especially one way, you're going to start seeing big problems. So what you would have, so we brought up the spatial thing, very good point. Another thing is that I'm not talking about is the latency link budget from the UE all the way round trip back to what could be your public safety packet data network that you've got to pull data from. Now, if it's FTP or something, you know, okay, not so latency sensitive, but if you're doing some kind of voice or video thing, you're absolutely right. And that's why I'd say this project I would like to see is something that could start telling users what's happening in terms of bandwidth and latency, because yeah, every single node here and every single medium is going to add latency to this. I mean, backplane across the server, the backhaul, you know, if you're up on satellite, certainly satellite will be the biggest drain on your latency link budget.
Looking at continuing with our deployables, we're going to look at their satellite coverage all the way out to the potentially all the way out to our users. Looking at necessarily maybe we may need to have spot coverage all the way out to very remote and rugged terrain. Being able to provide satellite coverage all the way out to the user, and have that satellite basically link out to that end user, and then link back to a local deployable coverage area that we might have, and then again back through the satellite over to the core.
Yeah, and by the way, that's not necessarily saying you're getting LTE directly from the satellite. You're getting some data connection. You're not getting LTE. That may change in the future, but I'm not sure if that's going to be anytime soon.
Okay, again, our pros and cons for the deployables to provide capacity when commercial or macro sites may be congested, or to provide that temporary coverage outside of our general, outside of our permanent LTE RAN footprint. We can, again, as Rob mentioned, we can carry that protocol stack with us to be able to have an onboard network, a totally self-contained network out there that we can have a small pipe or a satellite pipe to reach back in for any critical data that we may need to reach into a server to reach. We can reduce our deployment expense out in areas where coverage may be rarely needed or may just be seldom needed. We can bring it with us in the event we have to go out there. They do operate similar in functionality to macro cells. These are self-healing. They have the ability to self-heal and form coverage among themselves with a mesh type system, and these are fully mobile platforms. Some of the cons, of course, is going to be limited range, limited number of users compared to what a macro cell would have, especially when we're talking about the difficulties of powering that equipment and creating a adequate backhaul, as Rob talked about. We may have a very large capacity out there being provided by this node. However, we have a small pipe reaching back into our network, or maybe possibly even no pipe, so that's going to create some challenges for us there. We have to take that entire platform out to the incident area, and this is going to require a lot more operational planning to be able to store, stage, deploy, and integrate these things if and when necessary. We can lean on some of our lessons learned from deploying sites on wheels in the land mobile environment towards that goal as well. And I would say absolutely would require dedicated personnel and resources to be able to roll those out.
Yeah, training, yeah, for sure. Do you guys have in Colorado now? Do you have I was in Kansas 2 weeks ago, and they were saying, you know, they're sitting at about a 4-hour response time with their current LMR deployables. Is there kind of a mechanism in place and places that this equipment can be stored around the state to do that? Or maybe they were joking with me. I don't know. It seemed pretty a good response time.
Short answer is yes.
Okay.
Don't forget, Kansas is flat.
Yeah, that's exactly. Yep. It's kind of funny. We'll show a plot of where people live in Colorado on the Eastern Plains, and he said that's what all of Kansas looks like outside of Topeka, Wichita, and Kansas City.
Okay, we've got here just kind of an overview of what the radio access network and the core transport integration kind of could look like, or could potentially look like. Taking local networks, going into regional networks, and reaching out to the national level for different types of resources and linking into databases and things like that. Rob, did you want to talk about any?
No, I think we'll address it in the next slide. I think here, this is the ideal never happens microwave topology.
Yeah, for sure.
This is so you know, a lot of microwave. I mean, obviously, when you try to have the ideal thing is to have fiber to every site, because you just continually light up wavelengths on wave division multiplexing equipment. But you do have to have microwave in some of the more remote sites. Obviously, Nirvana is trying to put the microwave on rings, but of course, when you start putting microwave on rings, and every link on that ring has to have higher capacity, because if you have a break at the edge of the ring, then the other sites have to take that capacity. This is kind of, if you had, these are design considerations, this is kind of a Nirvana scenario. When you get in those boomer and high sites, you know, the chances of being able to be on rings may be less. You'll have sites that just simply don't have line of sight to more than one site, so you'll have to daisy chain them. You know, in those cases where you do have, you know, daisy chain, you know, you want to keep the two-way annual availability propagation of, you know, 4 nines and a 5, or 5 nines if you can. You know, use of space diversity, 1+N, monitor hot standby equipment. How you size the backhaul per site is really going to depend on your usage profile. So you have 3 sectors, and if you would assume that each sector could, in 10 megahertz, could theoretically do 50 megabits down and 25 megabits up, you know, you could have 75 megabits per sector, but you've got to look at what's the probability of loading up a sector that much, and what's the probability of all 3 sectors being loaded at the same time. So do you want, you know, once you put IPsec and some overhead on this, do you want 100 meg per sector at each site? You know, 300 megabits per site is getting very hard with microwave. I mean, you're going to have to meet, you know, your crane models for rain. It's going to be very hard to get that 4 nines and a 5 or 5 nines with that, obviously. So that's going to depend on the usage profiles that you come up with and consulting with users and what their applications are. You would expect, you know, so you'd probably take all 3 sectors, 3 times 75, and multiply it by some factor, maybe 0.3, 0.5, 0.6, 0.8. You know, you've got other access technologies at the site. Those will probably be kind of negligible compared to the capacity that LTE is going to demand. The cell range, okay, I talked about that, is going to be different, obviously, depending on the site. Obviously, spacing on the tower loading. You know, I know a lot of, I don't know, you know, the LMR site. You know, what if it might be at 100% wind loading right now. You know, and if you have to put a lot of microwave on it, you know, you have to reinforce the tower. That's expensive. So these are just, I mean, I've rarely ever seen microwave networks. Everything's on a ring, even financial institutions that actually pay loads of money to build backup microwave networks as a backup to fiber because they want it to be even faster, and they've got gobs of money. They still can't put every single site on a ring from, you know, New York to Toronto or for financial transactions. So. And then this is kind of a conceptual thing. This is just making the point, you know, you've got these different radio, gosh, I don't know what happened with the text there. Sorry about that. It's got clipped a little bit there. You know, these, the point here is that your serving gateway and your packet gateways, which could be one box or could be a virtual machine on a server, they're really taking your payload, your traffic. So you really want those network elements pushed out to the edge of your network closer to your RAN to offload your traffic. Plus, you know, when you talk to whoever may be providing your core network, you would like to co-locate their core equipment probably in data centers or network-to-network interface locations that you have your packet data networks. So you reduce the latency, you get the capacity where it's needed offloaded at the edge of the network. Also, a lot of public safety do VPN, you know, and that can affect network performance. So again, you want to really offload the capacity to the edge of the network as much as you can. The signaling, you know, you can probably bring more into the core because it's not going to be a big capacity demand to process signaling and priority and that sort of stuff in a nationwide core. Now, Colorado could look, so you could have Colorado and Wyoming looking something like this. You know, if you're American Samoa or you're Hawaii and you're significantly geographically displaced from the 48 states, you know, you might want to have all of this stuff sitting in that location. You might not want to bring extremely minimal resources back to a core that would be in the United States. So that's just kind of the general point of this slide. We're going to take a break because we're about, I think, about the halfway point. Does anyone have any questions so far, or